Okay, welcome everyone. So this morning we're very happy to have David Skinner tell us about topological strings on the beach. Take it away.
So thanks very much, Andrea. Thanks, Dario, for the invitation to come. Yeah, I'm going to talk about some work that hopefully will appear very soon, which I've been doing together with Roland Bittleston, my PhD student Simon Herverlein, and Surya Raghavendran. And I should say it's certainly been Roland who's been the hero of the story. Wow. Okay, so the starting point is this particular nonlinear PDE known as the KP, Kadomtsev-Biashvili equation. And this describes the evolution of water waves in 2+1 dimensions. So you should think of the surface of water as being described by x and y, and then as time goes on, the height of this water u just can vary. Okay, so we've got some waves in water. And it's a famous example of an integrable system in 2+1 dimensions. So in particular, if these water waves, if we reduce one dimension, turning off the y dependence, this thing just reduces down to KdV equation. These waves, as described by KP, are in a particular regime. In particular, that KP equation is certainly not invariant under rotations in the xy plane. X and y appear very differently, as you can see in that equation. And so there's a sort of preferred direction. It turns out that these describe waves that are traveling predominantly towards the beach. They don't have to be traveling directly towards the beach. They could be coming in at some angle, but they have to be traveling towards the x direction, not away from the x direction, or not perpendicular to the x direction, something like this. Now, as an integral system, we'd like to sort of fit this into some sort of classification of integral systems. And there are at least two broad classification schemes, two that I want to talk about today anyway. One is that all integral systems somehow have got some sort of twisted description. Won't surprise you that that's the sort of classification scheme that I like. And another, which perhaps also won't surprise you, is that they come from some sort of mixed topological holomorphic Chern-Simons theory, the more recent classification introduced by Costello, Yamazaki, and Witten. But at least to date, this KP equation has not really fitted into either of these classification schemes. And so partly what I want to do is to see how it fits into this framework that describes many, many different integral systems. In particular, how does this one fit in? Now, that KP equation as normally written, if you look it up on Wikipedia, hey. Yeah, so is there a lax pair formulation? And yes, there is. Yes, there is. So you can do that here. Yeah. We'll introduce a spectral parameter. We'll see how all that goes. Yeah. I'm sure everyone has their favorite, but what you just said there absolutely does come out of this sort of situation as well. Okay, so that KP equation, as we wrote it down, isn't itself an Euler-Lagrange equation. It's not something that comes out as the unique equation of motion of any action, as far as I know. But if I introduce a field phi, and I write that action, which is just some action with a standard, first term is just some standard kinetic term in 2+1 dimensions, and then there's a modification of the kinetic term which will involve that fourth order derivative that'll give us the fourth order derivative that we saw in the KP equation, and some sort of cubic interaction, again involving derivatives of this field in this particular x direction. Then the equations of motion for this action are these, and that's not immediately the KP equation, but if I differentiate again with respect to x, then if I identify the field, the height of the water u, as the derivative of this field phi with respect to x, then u will obey the KP equation if phi obeys this equation. So this is a sort of a potential form of the KP equation, if you like. Just a strange feature is that the kinetic term, it's a standard kinetic term in 2+1 dimensions, but with respect to a metric that looks like this. And so in particular, sort of surprising from a point of view of waves, x and t here, with respect to this metric, are both null directions. although the theory is, of course, not Lorentz invariant or not rotation invariant, depending on how you prefer to think of it, because of the interaction and dispersive terms. Yes. Yes. Oh, sorry. Okay, so I changed slide. So exactly what numerical factors you put in front of the terms of this action actually have no particular significance. We can always rescale them away. The ones in the action that I wrote just a moment ago, those are the ones that will give you the KP equation as you'd find it, say, on Wikipedia. But you're free to rescale coordinates, rescale the field in various ways, and get equivalent actions. In particular, if I rescale the coordinates by some parameter q, then I end up with some action which looks like this, which is totally equivalent. I think I maybe have introduced some numbers as well. But in any case, these actions are totally equivalent after rescalings, but it's going to be helpful for me to think of the action this way because it introduces this parameter q, which I can think of as like a coupling constant. In particular, it now appears in front of this interaction term. And this coupling has mass dimension -1 with fields normalized like this. And so it's a non-normalizable coupling. We would expect this thing to be if I was to quantize this theory, we would expect this to be a non-renormalizable theory. Okay, so these are shallow water waves, so they're exactly what you would see if you go to the beach. But why on earth am I telling you about them in a conference on celestial holography? Well, it turns out there are lots of connections. Firstly, as an integrable theory, you would expect that there's an infinite set of conserved charges associated to this system. And in general, these conserved charges will be non-local. They will be the charge will not be a single integral over some constant time slice of space-time, but rather multiple integrals over non-local combinations of fields at various points. And because of that non-locality, the explicit form of these charges in the way that they're normally written is rather complicated. So in exactly the same way as in celestial holography, it turns out we'll find a much simpler way of getting to what these charges are, or symmetry is, by considering them not as sort of normal charges, but as asymptotic charges. Okay? In particular, by considering collinear limits in perturbation theory, we'll be able to find a much simpler understanding of what the symmetry of these equations really are. So just as in gravity or in Yang-Mills, we'll consider a scattering process in perturbation theory where we take two external particles to become collinear, and the corresponding Feynman diagram will develop a pole, and the residue of that pole will tell us about the symmetry. Now, again, because we're in integrable theory, because we've got this infinite set of conserved charges, the Coleman-Mandula theorem is going to imply that the S matrix is trivial. We only know that this is a classically integrable system. Nobody's ever told you that quantum water is integrable. So we only know that the tree level S matrix is trivial because we only know these charges are going to be conserved at the classical level. So there's not going to be any S matrix in this theory, but there will be non-zero form factors. You could imagine putting a rock in the middle of these waves, or a plug hole or something, some operator that changes the behavior of the waves. And in the presence of that operator, there will be non-trivial scattering in the presence of the rock. So there will be non-trivial form factors, and so really we'll be considering these Feynman diagrams for form factors. Okay, maybe I shouldn't have said Coleman-Mandula, but just the presence of these infinitely many symmetries which do not commute with Lorentz transformations would mean that the S matrix is trivial, as in any integrable system. At the classical level, yes, modulo the stuff that we know that we're talking about. Yeah, so yeah. You know, for generic external momenta, let's say, yes. Okay, so what are our external states in perturbation theory? Well, of course, we should look at the free equation. The free equation is the standard wave operator, but with a modification coming from that dispersion term, that higher, the fourth order derivative in a particular x direction. And we can still solve these, of course, using momentum eigenstates, But the presence of the dispersion term means the momentum eigenstates have got an unusual dispersion relation. K squared is no longer 0, it's not null, but instead it's proportional to the x component of the momentum to the 4th power. Yes.
In this theory, we don't have any gauge symmetries, right? So these conserved quantities are not arising as some large gauge symmetries at all. As the usual, that's the usual interpretation in celestial or any
If I gave you
holographic.
the Plabansky equations,
Yeah.
what would you say?
In
Self-dual gravity.
Well, that's the diffeomorphism symmetry. The large diffeomorphisms would give rise to the W infinity algebra.
I think you can think of this in a similar way.
This is some gauge fixing of some gauge invariant here, and these are residual or some kind of gauge symmetries.
Yes, yes. Well, certainly. So in 3 dimensions, we can solve this using spinors, just like you can in 4 dimensions. So at the moment, let's just ignore this dispersion term. So in 3 dimensions, our 3-component momenta can be represented as a symmetric spinor, symmetric bispinor. And if it was just null, if k squared was 0, then usually in 4 dimensions, you'd say that meant you have a lambda and a lambda tilde. But because it has to be symmetric in 3 dimensions, they both have to be the same thing if it's null, right? So it would just be proportional to the same 2 copies of the same spinor will give you a null spinor, a null vector in 3 dimensions. Okay? And I've introduced some parameter omega that just allows me to absorb any scaling of these symmetries, of these spinors. So if I rescale my kappa, then omega should rescale to compensate the scaling of this kappa squared. Okay. But because of this dispersion term, there's a correction to this, which turns out to look just like that, where there's some sort of reference spinor iota here, where all this reference spinor does is it picks out this direction d by dx. Okay, so remember I said that d by dx was a null direction. That means there's also some null vector that I can dot into my 3 derivatives, and that null vector again has to be a symmetric bispinor, and I just call that bispinor, that fixed bispinor, iota. Okay. So in 3 dimensions, in Minkowskian signature, this spinor kappa should be real, and it determines, you can think of it as determining a point on the celestial sphere, which in 3 dimensions is really a celestial circle. And this parameter omega is then useful because I can view this combination, so omega times kappa squared dotted into this reference spinor, as the particle's energy. Okay, so just as in standard celestial holography, I can now expand my field. So this is my momentum eigenstate, for example, with that funny dispersion relation. I can expand it in powers of the energy, so expand it in powers of omega, and I'll choose to do that this way. And then the coefficients of that expansion are what we'd normally call the energetically soft modes. Now, we said that omega and kappa were defined up to this sort of mutual scaling, and because of that, if I rescale omega here, this soft mode has to compensate for that. And what that's telling me is it transforms as a quasi-primary operator on the celestial sphere, the celestial circle, of weight m-1.
So you're saying this Minkowski space, there is the preferred null direction. Am I correct?
Yes. So the KP equations that we started with weren't Lorentz invariant, or weren't even rotation invariant. They had this preferred direction x.
Yeah, but
right?
there's
and that direction was null with respect to the metric that we used.
Yeah.
And so I'm calling it,
but there is only one null preferred direction. There is not a verse or something.
Correct.
Yeah.
Yeah. So I mean, if we go right the way back to the KP equation where we started, right? So this term and this term would just be the standard sort of wave operator in Lorentzian signature with a pair of null coordinates x and t, right? And then everything else singles out just the x direction. So it's only the x direction that's breaking the symmetry. Okay, so we expand momentum eigenstate in these soft modes. The soft modes transform in some way under this rescaling, which is really telling me that they transform like a quasi-primary operator of weight m-1 on the celestial circle. And again, we can identify these as some state in some sort of chiral algebra living on the celestial circle, or really its complexification, a Riemann sphere whose equator will be the celestial circle. And as usual, what we want to do to extract the algebra obeyed by the chiral algebra obeyed by these operators is take the collinear limit, i.e. take two kappas of two different external particles, say 1 and 2, to become collinear. So take their kappas to become proportional, and understanding what happens to what the singularity of the form factors is in that limit will tell us about the algebra obeyed by these soft modes. Okay, so let's compute that. Just because the expressions get a bit messy, let's start by doing it just to leading order in Q. So leading order in Q, remember the higher order, the fourth order derivative came with a Q to the 4, a Q squared. So that came with a Q squared, and the thing that came with just one power of Q, that was just the interaction. So to working just to linear order in Q, this Q comes from just this interaction vertex here, and then all the other Qs that will be in my external states or in my propagators coming from the modified dispersion relation, those I've all set to 0. So essentially I'm in the dispersionless limit when I do this. And then what you get for this diagram, so these two momentum eigenstates, now standard null momentum eigenstates, joining to form a propagator that propagates to some point x, where it meets whatever the rest of my diagram is, it turns out they look just like that. Where these funny, this 1, 2 squared in the denominator is basically just the propagator, p1 plus p2 squared, written in 3 dimensions. The fact that you get a double pole is, again, because 3 dimensions, our null spin was the same, our null momentum was the same spinor twice. That's why we get this double pole. And this weird numerator factor is coming because we had some weird derivatives acting at the vertex, right? The vertex was a particular derivative of the field, the x derivative of the field, some power. So that factor here is the x derivative of the external state here. This factor is the x derivative of this external state here. And this factor is the x derivative of the propagator. Okay, so now to understand what happens so we've got a nice singularity as 1 and 2 become proportional. Various places that can be cancelled by. There are various factors of 1 and 2 in the numerator, and there's also factors of 1 and 2 hiding in the momenta of the propagator in position space at the x end, where it joins the rest of the diagram. So in particular, expanding out this momentum eigenstate as K1 becomes close, as kappa 1 becomes close to kappa 2, you find that it's equal to this. So the leading term is just 1 times a modified momentum eigenstate where the momentum is entirely in the direction of kappa 2, but there's some sort of rescaled energy because we've now got the energy of particle 1 together with the energy of particle 2. So the omegas are sort of getting shifted by that. But then there are subleading corrections, and in particular, there's a correction that's got that's just first order 0 when 1 and 2 become proportional, which looks like this second term here. And then there'll be higher order corrections with higher powers of angle bracket 1, 2 in the numerator, but those things are just going to give me some regular contribution once I go there. So they're not going to be interesting for the OPE. Okay, so we just plug this in for the exponential. That reads off the singularity as angle bracket 1, 2 goes to 0, as these two particles become collinear. But we really want a statement in the soft mode, so we should also further expand in the powers of omega 1 and omega 2. And if you do that, remember these v twiddles they're just some rescaled version of the soft modes of the particle. What you find is they have an OPE which looks like this, where these z's are just local coordinates for the kappas, and they look like this. And this OPE is W1 plus infinity. So if I take the Laurent expansion of these things in the Z's, that will be W1 plus infinity. Probably I should have gone further and put it in its familiar form. It's not, I emphasize, it's not the loop algebra of W1 plus infinity as we're familiar with in 4 dimensions. And again, that's easily to understand. In 4 dimensions, you really have 3 parameters labeling your null momentum, right? And so your W1 plus infinity has got 2 labels, 2 integer or half integer possibly labels, an M and a P or something like that. And then in addition, you have some Z dependence, which gives you the loop of W1 plus infinity. Now we're just in 3 dimensions, so we should expect 1 fewer label. And indeed, we've just got an M and an N label, and then we get our other discrete label by taking the Laurent expansion of the Z's, and there's no further loop algebra from that. So you just get W1 plus infinity. turning the dispersion back on, so what we've done so far was just in the leading limit of small q. So putting all the q dependence back, we now modify the propagator because we've got a modified kinetic term. And that's this q squared piece down in the denominator. And also the k's in the external momenta now have some q dependence. They're no longer just null in the normal way, but they've evolved that modified dispersion relation. And now expanding that out because of this more complicated q dependence and the more complicated denominator and the more complicated dependence of the exponentials on the q's, we get a more complicated OPE, whose leading term is the same thing that we had before, but now involves many, many derivatives, an infinite series essentially of derivatives acting on the right-hand side. And you know, maybe the details won't particularly matter, but these derivatives look like this. If we've got an infinite series of powers in Q, I think I've dropped an overall factor of Q, but the lowest term here is essentially the algebra that we saw before. Well, it's exactly the algebra we saw before, but then there are infinitely many higher corrections. And what they're doing is deforming little W1 plus infinity that we saw before to capital W1 plus infinity. Well, it's a formal power series in Q. It's a formal power series in Q. It has, for any fixed power of Q, for any fixed value of L, then these number of derivatives you get is fixed, right? So there are just L plus 1 derivatives. But as we expand to infinite order in Q, which of course we'll get from expanding this, then yeah. So you should think of.
Sorry, but this is going to be big W1 plus infinity now, is it?
This is big W1 plus infinity.
Yeah. So it's yeah. Okay. So it's sorry, the Moyal. Yeah.
So these algebras are the algebras that, through a lot of work with non-local charges, people have found as non-local expressions in KP. The capital W1 plus 1 plus infinity algebra is indeed the symmetry algebra of the conserved charges in the KP equation, and little W1 plus infinity is what you get from looking at its dispersion limit. That's been known before, in particular in the dispersionless case by Lionel, although not from this sort of celestial collinear limit approach. As I said before, let me emphasize that we really get W1 plus infinity, right? Not its wedge subalgebra, not its loop algebra, not anything else that we may have. These really are these capital W or little w algebras. Now, of course, that's reminiscent, very similar to things we know in celestial holography. In celestial holography, we get the loop algebra of the wedge subalgebra of little W1 plus infinity as the asymptotic symmetry of self-dual gravity in 4 dimensions. And similarly, we could get the loop algebra of capital W1 plus infinity if we make that self-dual gravity non-commutative, if we do a sort of Moyal deformation of the Poisson bracket that appears in, for example, the Blavatsky equations. These relations, the fact that these similar algebras are arising is definitely no accident. I mean, I'm not saying that pejoratively. It is clear that there is no accident. The relation is well understood by Lionel in particular in the dispersionless case. So let me start to talk about that. So now let me build in a way of fitting this into the standard framework, well, one of these recent frameworks of integral systems. So in the case of integral systems, Costello, Yamazaki, and Witten introduced a beautiful approach to understanding them based on some sort of variant of Chern-Simons theory on some space that includes the space where the integral system lives, but also includes, as part of the geometry of the space, the spectral parameter as well. In the original case that they considered, they had a certain variant of 4-dimensional Chern-Simons theory, which lived, it was a mixed topological holomorphic Chern-Simons theory. So it knew about some smooth topological surface, let's just say R2, and that surface was where their integrable system originally lived, together with some complex direction, say just the complex plane, which would be the space parameterized by the spectral parameter, but as well as the normal Chern-Simons 3 form, in order to write an action on this 4-dimensional space, they needed to introduce by hand some sort of meromorphic one form. So this is something that on the complex plane, in the simplest case, it would look just like, say, dz in the obvious way of the coordinate. So you would wedge your Chern-Simons 3 form against dz. And wedging it against dz means that the Chern-Simons 3 form only knows about the z bar direction, so it's going to be polymorphic in the z complex plane, but still topological in the remaining two directions, the sigma direction. As an example of what this was good for, we could construct, as usual in the Chern-Simons theory, we could construct line operators, in the simplest case just Wilson lines, and these Wilson lines, from the point of view of the topological directions, R2, they would just look like normal Wilson lines, but they'd sit at different points in the z direction, so these things would lift and would sit at different points in the z direction. And then the fact that I can pass, for example, this red line across the intersection in the plane between the green and blue lines to get something like this. So this, this is where I've kind of dragged that red line over to the right. This, from the point of view of the integrable system, would be a Yang-Baxter equation, the fact that these two things are supposed to be the same. And it holds in this theory precisely because nothing singular happened as I dragged one line past the other two, because they were actually separate. They were sitting at different heights, if you like, different points in the Z complex plane. And this is the origin of integrability for spin chains, from their point of view. And all the different spin chains you can get, and all the different sort of integrable systems you can get in this framework all come from choosing different types of one form. So we don't just have to choose dz, we could put in some poles, we could put in some zeros, we could change the gauge group, we could impose different boundary conditions on the gauge field at those poles and zeros. All of those different choices lead to different families of integrable systems. That's why this is a sort of classification framework for all of them. Now in our case, to describe KP, we're going to find a similar sort of Chern-Simons theory, again, on the space R12, where the KP equations live, together with the space of its spectral parameter, the Riemann sphere. Okay? And I'll give this space coordinates, well, the x's, which are symmetric in a pair of spin indices. They're, again, my normal three-dimensional coordinates. And then lambda, as usual, will be some homogeneous coordinate on the Riemann sphere. Okay? And I can view this spectral parameter as a complexification, this Riemann sphere as a complexification of the celestial circle. The equator of this Riemann sphere will be the celestial circle in 2+1 dimensions. Now, how are we going to get a mixed topological holomorphic theory that's going to describe the KP equations? So as usual in an integral system, we want the dependence on the spectral parameter to be holomorphic, but we can't ask that the dependence on 3 dimensions is entirely topological, because the KP equations are certainly not topological equations, right? They know about the location in x and y.
Is there?
Yeah?
Yeah, so is there any intersection between this construction and the twistor construction of self-Joule mills or self-Joule gravity, or they are describing completely different?
It's of course very similar. So there, the self-Joule Yang mills would live in 4 dimensions, and the spectral parameter would be a Riemann sphere. So we'd have a complex direction, which is the Riemann sphere over our 4 dimensions. We would have not a meromorphic one form, but a meromorphic or maybe even holomorphic, well, depends on which framework you want to use. A meromorphic 3 form, which would look like D3Z, the normal twistor measure, maybe with some poles. You'd write the Chern-Simons 3 form against that, which would now be a holomorphic Chern-Simons 3 form. And so, yes, absolutely, it fits into that framework. These things are very close to
In this sense,
sure.
okay, thanks.
Okay, so to find a way of thinking of R3 as a sort of a combination of complex and topological directions, we'll split it into a complex plane and a real line, but the way we'll do that split is going to vary as we move around in the spectral parameter direction, the CP1. In particular, at some point on the Riemann sphere, I'm going to choose this vector to be my holomorphic vector in R3. So whatever my point is on the Riemann sphere, I construct a null vector d by dx, and think of that as my holomorphic vector. The same thing with lambda bars will be my anti-holomorphic direction, and the mixed one, which is not a null vector, that at that point on the Riemann sphere will be the topological direction. Lionel will be wincing that I'm trying to tell a Euclidean story in Lorentzian signature, but let me enjoy my moment. So in this, with this With this choice, the spin bundle, this 5-dimensional space, which is just S2 or CP1 cross R3, has got a transverse holomorphic foliation. At each point, we've got a sort of topological direction, and the planes transverse to that are locally copies of C2, the rest of the Riemann sphere direction, together with this complex plane sitting inside R3. Now, this is, of course, very close to a version of twistor space. It won't be surprising to you lot to hear that I'm going to tell you something about twistor space. But since we're in 3 dimensions, the relevant twistor theory is actually known as mini twistors, just because we're in 3 dimensions rather than 4. How does this work? So for C3 rather than R3 for now, the mini twistor space is the tangent bundle of the Riemann sphere, so O2. So it's got two sets of coordinates. One is our lambdas that we know before. Those are just coordinates on the Riemann sphere as usual. And then there's one further coordinate, mu, which is a coordinate on the fiber of the tangent bundle of the Riemann sphere, and it scales like lambda squared. And how is this related to space-time? So if you give me a point in C3, then that will determine a section of O2, a section of the Riemann sphere, by an incidence relation, which in 3 dimensions looks like this. So again, what this is saying is if you've given me x, a point in C3, and you've given me your lambda, so you tell me where you are on the Riemann sphere, I'll tell you what value of mu you've got. And so I'm giving you this section. This is an embedding of the Riemann sphere inside the total space of O2. Now, if I've got any 2 sections, so suppose I've got this equation for x and I've got this same equation with the same mu and the same lambda for y, then those 2 sections will meet whenever the difference is 0, which would just be this equation, and that's a quadratic equation in lambda, so that will always, unlike in 4 dimensions, this will always have 2 roots. And we decide that the 2 points are null separated in C3 if those 2 roots coincide. So in twistor lines in 4-dimensional twistor space for 4 dimensions might just miss each other. Here, these twistor quadrics always intersect each other twice. What makes them null separated isn't the intersection, but the fact that those two intersections coincide. Okay, so that's it for C3. Of course, we want to be in Lorentzian signature, and so we put a complex conjugation on mini twistor space, which just literally takes the complex conjugate of each of these points, and in particular, it fixes the equator, the celestial circle, in the lambda direction. And then points that are not just in C3, but are really in real Lorentzian spacetime correspond to sections that are fixed under this conjugation. And now, okay, still it's the case that if the 2 roots of this equation, when x and y are now points in real Minkowski space, if those 2 roots coincide, then the points are null separated. But now if they're distinct, then depending on whether both roots are real or whether they're complex conjugates of each other, so depending on the sign of the discriminant, essentially, we can either declare those points to be space-like or time-like separated. So we really learn about the metric from this structure. How much of this do I want to say? So if I differentiate the incidence relation holding mu and lambda fixed, then I get this equation. So given a point in spacetime, we get this Riemann sphere in the mini twistor space. Suppose I fix a point mu and lambda in the mini twistor space, and I look at how can I vary x and still solve my incidence relation. So the derivative of the incidence relation at fixed mu and lambda looks like this. And that tells me that dx, so any way I move from my starting point, has to be constrained to be of this form. It has to be proportional to lambda, so that when I contract it with lambda, it vanishes, and then there's some free one form d nu, at least in the complex. But for this complex 2-plane to intersect real Minkowski space, then there are various conditions, and whether it's so if dx wants to be real, then you've got various choices as how that might happen. If lambda itself is complex, for dx to be real, d nu has to be proportional to its complex conjugate with some real variable s. Okay? And so that tells you then that dx is totally fixed, and it describes a time-like geodesic. So we've got a variable parameter s that just moves us up and down this geodesic in this fixed direction. On the other hand, if lambda is already real, then d nu isn't constrained to be anything other than again real. And so now the complex 2-plane intersects real Minkowski space in a real 2-plane, And if you look at what the metric on that real two-plane looks like, you'll find that real new two-plane is null, contains a null direction. Okay, some subtlety when in various situations. Okay, so we can put all this together in a double fibration. This double fibration, the main player is this spin bundle, this 5-dimensional space, which is just R3 cross P1. Of course we can project, sorry, just R3 cross CP1. Of course we can project down to our space-time just by forgetting the spectral parameter, forgetting the lambdas. But we can also project down to mini twistor space, and again, modulo some subtleties, the fiber of this projection is just this topological line. Now, mini twistor space has got a natural two-form of weight 4, so rather like in holomorphic two-form to get a Poisson bracket, just the inverse of the holomorphic inverse of this omega guy, which looks explicitly like that. And that Poisson bracket is going to play a starring role in our theory. Now, to attain the KP equation, rather than just its dispersionless limit, we don't actually just want the Poisson bracket, rather we want to Moyal quantize this Poisson bracket, following ideas, suggestions of Ian Strawn. And how do we quantize a Poisson bracket? Well, in Moyal quantization, the first thing you do is you take your Poisson bivector, your Poisson bracket, and split it, write it as a pair of commuting vector fields. And then, given these pair of commuting vector fields, you define a star product between any two functions to be, well, firstly, you just imagine the functions as living in separate variables, if you like, in separate spaces, and you take the exponential of these two vector fields that we split our Poisson bracket into, where whoever's the first one here always acts on F, and whoever's the second one here always acts on G. And then at the very end, having worked out this infinite series of various derivatives, you just multiply them together. In other words, you just say, actually, they always lived at the same place. But you do that at the end. Okay, and if you expand, what you get, the leading term is, of course, just the standard product. We take the 1 from the exponential. Where we take the q from the exponential, that'll just give us each of these functions differentiating in f and g once, and that's the Poisson bracket. But then there's an infinite series of higher corrections in q from this Moyal product. And this parameter q is the same parameter that we've seen before, and here it's controlling the scale of the non-commutativity. Now, with our Poisson bracket, the one that we've just had by inverting that meromorphic two-form, the natural thing is to choose one of these vectors to be the thing that differentiates in the lambda direction, the other one to be the thing that differentiated in the mu direction. I've included factors of this iota lambda contraction just to make both of these things weightless. And then you get a star product on twistor space, which for the basic coordinates of the twistor space looks like this. Okay, so now the twistor space coordinates don't commute with themselves. We've got a non-commutative mini twistor space. Using that, we can now construct our holomorphic Chern-Simons theory, a mixed topological holomorphic Chern-Simons theory in a non-commutative way, but we want to write that not on the mini twistor space itself, but rather on the spin bundle. So what I'm going to do is pull back that meromorphic two-form back up to the spin bundle. I'll abuse notation by not keeping track of the pullback. I'll still call it omega. And then wedge it against the non-commutative Chern-Simons 3-form that we've got built using our star product from twistor space. To do that, I've had to lift the star product, these vector fields which naturally live on twistor space, up to the spin bundle, and there's a lot of freedom in that, and I'll talk about that in just a moment. But for now, let's just imagine we've chosen some way to lift them, and this is what I'm doing. So this is abelian, but non-commutative. And so in particular, the leading order term here is of order q, because if I just replace these star products by standard wedge products, then because we're in the abelian theory, that cubic interaction would zero, because it would be anti-symmetric with no color factors in exchanging any of the a's. But because of the star product, it's not zero. Okay. So as in the 4D Chen-Simons theory of Costello, Yamazaki, and Witten, this A is only a partial connection. It only involves the components which survive wedging against omega. So not all components of A in 5 dimensions survive, because we're going to wedge the whole action against omega, and that'll kill lots of components. And the ones that survive, there are 2 directions. This is a 2 form, so there are 3 remaining components of A which will survive. Let me split that into something I'll call A bar, which has got 2 components, which is a 0-1 form on the mini twistor space, transforms as a 0-1 form on the mini twistor space, and the remaining bit, which is the component of A that points along the fiber of the spin bundle over mini twistor space. There are also some boundary conditions. This omega, remember, we divided by iota lambda to the power of 4, so we introduced some poles, and for this action to be well defined, we need A to obey some boundary conditions at those poles, and the simplest situation is just to say that A vanishes to second order on that pole. Okay, what do the equations of motion of this action say? Well, they say that the omega wedge the curvature of, built in a non-commutative way, so this would be dA plus A star A equals 0. If I gauge fix and work in the gauge where the vertical component of this gauge field is 0, so the only remaining ones are these ones that as functions live on the spin bundle, but as 0-1 forms point purely in the mini twistor directions, then what do these equations say? Well, the sort of mixed 0-1 vertical component just reduces to the statement that the A bar, the remaining components that I haven't set to 0, have to be independent of the vertical direction. In other words, they're pulled back from mini twistor space, and the 0-2 form part of the curvature, the bit where both indices point in the mini twistor direction, just tells me that I've got some sort of abelian, so rank 1, holomorphic bundle on mini twistor space, but on this non-commutative mini twistor space because of the presence of that star product. Now, as I said, in order to write that action down, we somehow had to take this star product which involved derivatives, and we had to decide how we're going to lift these derivatives up to mini twistor space, and there's a huge amount of freedom in that. Much more than Lionel currently suspects. Okay, so of course, because the normal amount of freedom would be that we've got some vector field pointing down here, and I'm going to lift it to a space that has got an extra dimension. So there's some freedom in how much of the vector pointing along this extra dimension, how much of the vector field pointing along the fiber should I add on to the vector that I've got on my base. Okay, so that's the bit that Lionel immediately expected I was going to talk about, but there's actually far more than that. Okay. And the reason there's far more is that the space of 0-1 forms, or the space of forms that survives wedging against omega, is much bigger on this spin bundle, is really defined as a quotient. Okay, so the space of holomorphic 1-0 forms, that's canonically defined out of all the forms out of all 1 forms on the spin bundle. Those ones that we'll think of as holomorphic, those are canonically defined because those are just anything that wedge to 0 against this pullback of the holomorphic 2 form on mini twistor space. So that holomorphic 2 form omega, my preferred omega from before, that already saturates the holomorphic directions. And so I've got 2 complex directions, 1 real direction in 5 dimensions. The omega already saturates the holomorphic part of the 2 complex directions. So what we mean by a holomorphic 1 form on the spin bundle is anything that wedges to 0 on that. And then the remaining forms, the 0-1 forms, are really just a quotient. They're any 1 form modulo things that wedge to 0 against that. But again, because they're defined as a quotient, I'm always allowed to add on a little bit of a holomorphic 1 form to something I'm treating as a anti-holomorphic 1 form. So there'll be a 3-dimensional space of these anti-holomorphic 1 forms, but it's defined just as a quotient. Equivalently, dualizing, what we mean by a holomorphic tangent bundle is likewise a quotient. Okay? So there's a canonical definition of what we mean by anti-holomorphic tangent vectors. Those anti-holomorphic tangent vectors are just anything that contract to give 0 when I contract into my holomorphic 2 form. Okay? Yes, but I'm on a 5 real dimensional space.
You're in 5 real, so there is no complex structure. In fact, that's what. So
exactly. So this is a mixed top. I've got 2 complex dimensions, so 4 real and 1 extra. What I'm saying is that the way what I'm calling a 0-1 form, maybe the terminology is not so great, right? What I mean is this is everything that isn't a holomorphic form, and so there's a 3-dimensional space of them. But how you define that 3-dimensional space is really defined as a quotient, because what I meant by a holomorphic form was something that wedged to 0 against omega. And so this is something that doesn't wedge to 0 against omega. But of course, that's defined. I can add on some amount of something that does wedge to 0 against omega and still be fine.
And just to fill in what Atul and I were just saying, this is not a CR structure either.
No,
It's because you've got topological directions.
Yes.
That's right.
Yes. So the holomorphic tangent bundle likewise is a quotient. So again, what we mean by anti-holomorphic tangent vectors are anything that contract to 0 against this preferred 2 form I've got. And what I mean by holomorphic tangent vectors in this case is anything else. And that's key because my star product involved a lift of something, wanted to be thought of as holomorphic vectors, but there's a lot of freedom in what I mean by holomorphic vectors. Now, if I make a choice, effectively choosing a section of holomorphic vectors, well, what that means is I just make a choice of what I'm going to mean by holomorphic vectors of these guys. Okay? Then we'll get a preferred set of 0-1 forms, whatever a dual to my choice of holomorphic vectors, and then there'll be a preferred Poisson bracket, a unique Poisson bracket acting on these types of forms. But it depends on this choice. However, the key point, which probably I shouldn't be spending so much time on, is that the theory is totally independent of this choice. In view of time, let me not give you the argument for why it's independent of that choice, but it is independent of that choice. And for example, Atul will be totally bored to learn. So normally in self-dual gravity in 4 dimensions, we've had trouble reducing, for example, the first Plabansky equation. There's an obvious action for the first Plabansky equation on twist, but because of frame dragging effects, etc., it's kind of tricky to reduce that to space-time. Really see it is. Okay? In fact, it's totally trivial. Okay, so because we've got this freedom, let me make a different choice. Okay? So I'm going to choose my holomorphic vectors to be these guys. So this one looks very similar to the one that we had before. It differentiates in the Riemann sphere direction, but now instead of differentiating in the Riemann sphere direction at fixed mu, as it would have done on twistor space, it's going to differentiate in the Riemann sphere direction at fixed point on space-time.
If you do that, why are you, presumably you'll try to use Liouville's theorem at some point to reduce things to space-time.
Yeah.
How are you allowed to do that if you pick an iota? Then you have to use a Liouville's theorem on the complex plane rather than the sphere.
I've got boundary conditions on what my field to obey. And once I've imposed those boundary conditions, Liouville's theorem is then on the complex plane.
Okay.
It just
It shifts which cohomology group you're looking at effectively because of the divisor. And what I'm going to choose as my other direction is not d by d mu, but d by dx, this preferred direction x in space-time. And again, this is an unconventional choice, although it's equivalent by the argument I didn't quite get around to showing you, because the push forward of these vectors is not, they're not holomorphic vectors when you push them down to mini twistor space. Okay? Nonetheless, if I take the exterior product of these two, the wedge product of these two, that does indeed invert this 2 form, and the corresponding Poisson bracket that you can build out of these 2 vectors does indeed, it is a Poisson bracket, it does in particular obey Jacobi identity. The corresponding basis of forms in which we'll expand our fields look like this. These are just dual to these vector fields. And so we can expand A and our kinetic operator in this frame. The boundary conditions on the field become a bit subtle. Let me not go into that. Okay, so now we're going to construct a different star product using this different bracket. I don't know why there's a dot into that one. So I'm just taking my new vector fields, the new vector fields that I'm treating as holomorphic, and expanding them that way. And so now with these vector fields, my star product is defined the same way as before, but now the vector fields are different. And now, what does this mean on the spin bundle? So because these vector fields, although one of them differentiates in a space-time way, the other one differentiates in the spectral parameter direction. And so space-time itself, a place where the waves live, is perfectly commutative. Okay? I'm not making space-time non-commutative. But what this star product does is it means there's some non-commutativity between space-time and the spectral parameter. So because one of these differentiates in the spectral parameter direction, the other one differentiates in the space-time direction, you get non-commutativity of this sort. Okay, so it's not enough to have a consistent star product if we want to write a Chern-Simons theory, because we need that Chern-Simons theory to be properly gauge invariant in the normal sense of a Chern-Simons theory. And what that means is we're going to need our kinetic operator to distribute nicely over the Chern-Simons, over the star product. So we would like it to be the case that our kinetic operator acting on a star product is just the kinetic operator acting on each of the terms in the star product, possibly with some minus signs in turn. But that fails to happen. With these vector fields, it turns out that at fixed x, this vector field that differentiated in the spectral parameter direction isn't holomorphic. It doesn't vary holomorphically. And that leads to this sort of failure of distributivity of the kinetic operator over the star product. And that would mean that if I just tried to use this star product to build a non-commutative Chern-Simons theory, it simply wouldn't be gauge invariant. It simply wouldn't make any sense. The classical equations of motion wouldn't be what you want them to be. Nothing would work. Fortunately, you can modify this not by changing the star product, but by changing the kinetic operator. So we add a new term to the kinetic operator, which involves these higher order derivatives in the x direction. And the point about this, what singles out this differential operator, is the fact that it does obey distributivity with respect to this new star product. Technically, what we've now got is a DGA. So now we can write down a non-commutative Chern-Simons theory adapted to this new frame. So I put this subscript L here to emphasize that I'm using this new frame, these new sets of vectors to define my star product, a new set of naught-1 forms to expand my field. And that thing is perfectly sensible as a Chern-Simons theory. Okay. All those things just say it's perfectly well defined, it's gauge invariant, everything that you'd want it to obey, it does obey.
To understand detail, that has a cubic derivative is still a Basel Leibniz rule?
Yes. Yeah. Well, it obeys the distributivity over the star product, and it's precisely because the star product has also got infinitely many higher derivatives that makes that work. Right? It's compensating for some failure of you know.
It's non-trivial that it even truncates to just a cubic order or something. Since it has to.
It's non-trivial that the failure of distributivity truncates. With the naive D, this is still an infinite series of derivatives because it's still got that star product there, but it's only got sort of 3 extra derivatives compared to the sort of basic star product. That's what's non-trivial, and that's what this D fixes up. You might also think, we'll get to that. Okay, so this is the theory living in this 5-dimensional space, which is S2 cross R3. How do we reduce it down to that action that I wrote for KP theory? Well, as usual, since we're just trying to reduce on this Riemann sphere, we just Kaluza-Klein expand. Okay? I don't truncate, I just expand it in modes on the sphere, keep all of the modes. However, because the action upstairs didn't know about any metric, it only knew about forms. It was basically a Chern-Simons theory, either holomorphic or topological, but a Chern-Simons theory. The only place any choice of metric, for which I've used to do my KK expansion by expanding in harmonic forms or something like this, the only place a metric enters is in gauge fixing terms. And so up to gauge equivalence, I'm completely free to say that I'll choose my metric so that the size of this P1 is really, really small. But in that limit, when the P1 gets really small, of course, all the higher KK modes become arbitrarily massive and decouple. So I didn't throw them away, but they're gauge equivalent to being absent. You know, in any other metric or any other gauge fixing, you'd have all those KK modes left downstairs, but they'd all just be BRST trivial. They'd all be pure gauge. So what you're left with is just the 0 modes, and those 0 modes, of course, live in some sort of cohomology on the P1, or the restriction of the kinetic operator to the internal space. And that equation ends up looking like this. So it's not all of the components of the field equation, which will be omega wedge the content of that bracket, but just the mixed space-time P1 ones, and I can do that by wedging against one of the space-time forms here. Okay, I'm running out of time. Well, perhaps that's perhaps that's it. So the key fact that okay, we go and solve this perturbatively. Okay, so I do some expansion of my gauge field in some sort of parameter epsilon, and again I'm going to keep all orders in epsilon. I'm not going to throw anything away. But the key point is going to be that because this thing involves the star product, this is only non-zero because of the presence of the star product. It must be at least of order q, and so it's going to come with higher power. This term for higher k is going to come with higher and higher powers of q, and they're going to that always comes because it's part of the star product. That's always going to mean that we're going to get higher and higher derivatives of the zeroth order term, and higher powers. Those derivatives are going to be accompanied by higher powers of this sort of reference spinor iota. In particular, if you look at what the expansion of my action is in powers of this new parameter epsilon and the parameter q, then you find that the coefficient of the various powers of epsilon and q come along with this many powers of the spinor iota and this many derivatives in the space-time directions. Now, when you integrate over the CP1, all of these spinors, which before you integrate over the CP1, some of them could well be contracted into lambdas, they could, or contracted into derivatives along lambda, or all sorts of things. But once you integrate over lambda, the indices on all of these spinors have to contract with somebody else because you've integrated out lambda. And the only options, there's no explicit x dependence, so the only, no explicit powers of x. So they can only contract either onto derivatives or onto each other. If they contract to each other, of course, that's the same spinor contracted with itself, and so we're going to get zero. So all that can happen, the only way we can get a term that survives is when the powers of that spinor contract with the derivative. But each derivative, each space-time derivative has got precisely two spinor indices, so it can absorb at most two alphas. And so we need that this number is less than or equal to twice this number, and that boils down to this inequality here. Right? Otherwise, some iota is going to have to contract with some other iota, and that term will just vanish. Okay? So there are very few terms which contribute. If you go through, there are actually only 3 terms that contribute. They're these ones, and in terms of the action, they look like that. Okay, so we get a standard kinetic term for the sort of leading order part of A, the modification to the kinetic term involving that third order derivative, and then just the leading order part of the star product, which reduces to the Poisson bracket. All of the other terms, they're still there on the spin bundle. There's infinitely many more terms involving all the higher derivatives, all the higher powers of epsilon, etc. But they're all going to integrate to 0 when we do the integral over lambda, because they've got too many copies of this spinor iota in them. Well, these 3 terms are now easy to understand. Right? This standard kinetic Chern-Simons term just becomes the standard kinetic term of the scalar field when you reduce down to space-time. This modified kinetic term in the Chern-Simons theory that we needed, that was there because we needed to have a right derivative operator which played nicely with the star product, that just becomes the modified kinetic term, this dispersive kinetic term downstairs with higher derivatives. This has got 1 derivative, and it ends up giving us 2 derivatives on space-time when you work it out. This has got 3 derivatives, it ends up giving us 4 derivatives on space-time when you work it out. And then that cubic interaction ends up giving you, it's got 2 derivatives, one at each slot of the Poisson bracket, and we again get 1 more derivative than that, 3 derivatives altogether. It gives us that cubic interaction. The role of all the remaining terms, all of the higher order stuff, I haven't thrown it away. It's there in 5 dimensions. But all it's doing is ensuring that I've got enough symmetry that this theory that lives in 5 dimensions is nonetheless equivalent to, not just reduces to at low energies or something, but is actually equivalent to, because of this enormous amount of gauge symmetry, a 3-dimensional theory. Well, they'd probably be related to what Atul was saying earlier. There's some sort of, some higher fields that you can remove by some diffeomorphism invariance or something like that in 3 dimensions.
But would they be some sort of higher spin type of objects or not at all? Or?
No, I don't think so. I think they'd all be written in terms of phi. Actually, maybe one thing that I could say. So this all came from using that alternative Poisson bracket, that alternative choice of holomorphic vectors on twistor space that I said I had the freedom to get, not the one that immediately came from lifting twistor space. If you try to use the one that comes from immediately lifting the twistor holomorphic vector fields, what do you get? Well, you don't get this action. You get an action that's just got a canonical kinetic term, because you've just got, because the twisted star product didn't need any modification of its derivative. But you don't get this dispersive term, and instead you get an infinite series of cubic interactions. They're always cubic in the field, but they've got many, many, many higher derivatives and also many, many powers of x. Those two theories look very different, but they're actually equivalent after a field redefinition. What have we gained? Well, I've got 0 minutes to tell you. So there we go. Okay, so one thing we've gained is that in this sort of twistor approach or Costello-Yamazaki-Witten approach, the reason you had integrability was because it was equivalent to this theory. As long as that equivalence holds, you should expect your theory, your space-time theory, to remain integrable. Why would that integrability break? It might break because your Chern-Simons theory, which was holomorphic, it was chiral, develops an anomaly at some loop order. But in our case, we're in 5 real dimensions, and certainly at one loop, there are no perturbative anomalies in 5 dimensions, in odd number of dimensions. So integrability of this theory cannot break, at least at one loop. Okay? So there can't be any scattering amplitudes at one loop, and you can see that from various points of view. So waves on the beach are quantum integrable, at least at one loop. So we wanted to check that. So these are the diagrams you have to compute. It's easy to check that as long as the 4-particle one-loop amplitude vanishes, which receives these things, all of the n-particle one-loop amplitudes also vanish. We have evaluated all of those 4 diagrams. Believe it or not, I can't tell you whether or not they actually cancel, because at least one of them is a total nightmare. But as I say, as long as the 4-particle one-loop amplitude vanishes, unitarity implies that the n-particle one-loop amplitude also vanishes, because we already know the trees vanish. We would also expect there to be quantum corrections to the chiral algebra. This quantum corrections will receive at one loop contributions from these 3 diagrams. There's sort of these 2 separating diagrams where I can cut a propagator and separate out the form factor from the sort of collinear factor, and then a non-separating factor. We know that the first 2 diagrams, these separating contributions, cancel each other. So there's no separating contribution, no separating modification at one loop, but the final diagram doesn't vanish. And so only this final non-separating diagram vanishes, and this thing deforms capital W1 plus infinity, not as a Lie algebra, but as a vertex operator algebra. The point is, it's not 2 states going to 1 state, so it's not a bracket that takes 2 elements and gives you 1 element back, as you'd expect in a Lie algebra, but it's 2 states going to 2 states, right? There are sort of non-linear terms on the right-hand side of the relation, and that's characteristic of a VOA rather than just a Lie algebra. There's a known VOA which does have this property and does deform capital W1 plus infinity. It's called calligraphic capital W1 plus infinity. And again, this is very similar to what happens in self-dual Yang-Mills and self-dual gravity. There's a nice origin for the algebra in twistor space where these algebras come from. Let me not go through that. There's a connection to topological strings. These things are supposed to be topological strings in some way, but maybe let me just get to the point. So these non-commutative Chern-Simons theories are the string field theory of some topologically twisted version of either string theory or M theory, depending on how you set it up. Now, perturbatively, that gives you the Chern-Simons theory, but non-perturbatively, these string theories will also contain various branes, and in twisted M theory, you'd have M2 branes and M5 branes. And these can wrap various things. So the twisted M theory initially starts in 11 dimensions, but you reduce it down to 5 dimensions, you get that Chern-Simons theory, the non-commutative Chern-Simons theory. Those branes can wrap various things in the 5-dimensional thing. And what should those branes be? Well, they're just solitonic solutions to the supergravity, if you like. So they should somehow be solitonic solutions in this non-commutative Chern-Simons theory, which amounts to saying they're interesting rank 1 bundles on, they're non-commutative monopoles on twistor space, but obeying these particular boundary conditions. And what are the solitonic solutions in KP? Well, they're exactly these water waves. So perhaps the final statement of the talk is that, it's hard to imagine a more abstract, non-observable thing than an M5 brane on non-commutative mini twistor space. But in fact, actually, it's the most observable thing in the whole conference, because it's just water waves on the beach. I'll stop there.
Questions? Okay, maybe I have one. As you go further out into the ocean, that will correspond to breaking the integrability.
Yeah.
or
Yeah.
it's-
So,
is
so,
there-
so the KP equation is a very particular series of approximations to ultimately Navier-Stokes. And the first thing you do is make a shallow water approximation. So the wavelength of your waves has to be much longer than the depth of the water.
But is there like a particular, in what you were describing, a particular breaking of integrability?
Oh, wouldn't that be great? Wouldn't it be nice if there was some sort of MHV term we can add on that gives you the full theory? And I have no idea. Yes, but not absolutely. But they're not KP, right? Absolutely.
Strong solutions the whole time for oil equation is $1 million. One question is the original algebra of any integrable system is just an infinite set of charges that commute.
Okay. Yeah.
So what happens?
So I'm not sure it's those charges I've been talking about. I mean, that's very much a Liouville-Arnold definition of what the integrability means. And I'm not, I mean, in particular, even classically here, they don't commute, right? We're getting W1 plus infinities.
That doesn't matter. But in general, the definition of it.
Yeah, absolutely. But how are they? Again, depends what you take as your definition. That's the Liouville-Arnold definition. Yeah, exactly. Right. Yeah, how they relate to this, I'm not sure.
I thought the W infinity generators would be the conserved charges in this case.
They are, but then they don't commute.
Yeah, they don't have to commute. They'll form some algebra.
Well, the Liouville story means that they do. Yeah.
They have to form
Just go around some torus in the phase space.
I can imagine that would form an involutive distribution. I don't know if they have to literally commute. Like that form an algebra.
But again, we're talking about integral systems, not about polar systems.
Yeah.
Integral systems, the definition is super easy, but is commuted. Otherwise, there are plenty of systems and algebra, and they are not integral.
Yeah. Yeah, no, this algebra is more like an algebra of sort of Backlund transformations, and you'd expect it to act transitively on the whole phase space, whereas the hierarchy of conserved quantities that underpin the Liouville theorem is some subset. I'm struggling to think of a good characterization of them. I mean, I sort of know what they look like in practice, but there's some abelian subgroup.
Yes. Okay.
Is there a version of a twisted type 2A M theory duality, or you could go to the type 2A frame and find a holographic?
Yeah,
cube?
I think so. I think well, so there are various ways of getting this theory, which is basically the same thing, but not on the spin bundle, but just on C2 cross R. One of those is a mixture of an A and a B model, but I think it's probably possible to get it for the pure A model in the presence of an appropriate background B field. It's probably something, well, that's something Davide told me, so it's probably something Kasia knows more about than I do, but I don't want to put you on the spot. But yes, I think you can get that particular action in many ways via many dualities out of many types of topological string.
Further questions?
Usually a topological theory doesn't have physical state. I mean, here you have solitons. These are physical state. How do you put together these two things?
It's not entirely topological. It's topological / holomorphic, right? So we had this 5-dimensional space that had 2 complex directions and 1 topological direction. So absolutely all we care about is cohomology. And that's what the Chern-Simons theory has brought us. But via Penrose transforms and things cohomology on a twistor space or cohomology on this 5-dimensional space corresponds to on-shell solutions of wave operators of particular type in whatever the space-time is, here 3-dimension. Yeah. And then, okay, so those are the sort of linearized fluctuations, just the local cohomology, but sort of other holomorphic objects instead of flat connections, so you know, gauge fields with vanishing field strength, we could have holomorphic connections, holomorphic bundles, and those are some sort of non-linear version of the cohomology. And here, those are what are giving you the solitonic waves in the ocean. In the beach.
Okay, if there are no further questions, let's thank David again.